Welcome to Philosophy Talk, the program that questions everything
except your intelligence. I'm John Perry.
And I'm Ken Taylor. We're coming to you from the studios of 91.7 KALW, local and innovative public radio for San Francisco.
Continuing conversations that begin at that lovely place, Philosopher's Corner on the Stanford campus, where abstract thought and coffee rule the day.
Yeah, and from there, via some kind of quantum flux, they migrate to the air, and from the air, via another quantum flux, they migrate to our blog, the blog.philosophytalk.org.
Now, Ken, I know that you, like me, has been studying quantum mechanics. Well, not exactly studying quantum mechanics, but reading readable books about quantum mechanics.
Skimming the surface of quantum mechanics.
And, you know, the first amazing thing about this is that we can know, we in the broad sense, can know anything at all about things so little that we can't even see them or smell them or feel them. We just have to infer it all from their little traces on a cloud chamber.
Well, that is a weird stuff, but that doesn't really distinguish quantum physics from, say, classical physics, because that was, in the end, about little tiny stuff and how it added up to big stuff, too. But this quantum stuff is really weird. I mean, sometimes a quantum thing behaves like a wave, and sometimes it behaves like a particle, and you can't really say it's wave or particle. It's kind of both.
And as I understand it, which isn't much, when you observe it or even measure it, there's something called the collapse of the wave function, and it goes from being described in a wave-like way to appearing as a particle. That makes no sense to me whatsoever.
Right. What do you think about a particle? You know, it's moving around on a definite trajectory, and if it collides with something, it hits it at a definite place. But you know, you do this experiment where you got two slits and you pass a photon through a divider, right? And so you make two photons and send one off that way and one off that way, and then they reflect it onto the wall, and you know what you'll get? You'll get an interference pattern. Waves have interference patterns. But just change that setup just a little bit. Put on one of the roots, say the right root, a detector that detects whether a photon's coming this way or that way. And you know what you'll get? You'll say, oh, if it detects a photon over here, the interference pattern will disappear, and it'll be like it hit the wall at a determinate place. And so, I mean, when you detect it, it's no longer a wave, and when you don't detect it, it's a wave. That's weird stuff.
You know, Ken, I mean, frankly, it'd be okay with me if the world of little tiny particles wants to behave, or little tiny waves, or whatever, can't make up its mind what it is, and it wants to just mess around however it goes, as long as it stays there real little and beyond my senses. But how does that complete weirdness at the level of quantum particles keep from percolating up to the level of things like you and I? I mean, if a little little photon can't make up its mind whether it's a wave or a particle, does that mean we could have a cat that couldn't make up its mind whether it was alive or dead?
Well, that's a good question, is because we're all just made of this quantum stuff. So whatever is true of us has to be true and because of the quantum stuff we're made of. But you know what? To answer your question, our roving philosophical reporter, Amy Standen, she went out and talked to an expert in quantum physics. She files this report.
So here's why quantum mechanics is such a mind-bender. Scientists have shown that the tiniest quantum particles do a very strange thing. They can be in more than one place at the same time. Now, the world is made up of these strange particles, but when you put them together into a loaf of bread or a person, for instance, to our eyes they look perfectly normal. But how can we do one thing if our parts do something entirely different?
Quantum mechanics is telling us that reality is just fundamentally, ultimately different from the way we perceive it to be.
Michael Strevens teaches the philosophy of science at NYU.
We see things in particular places all the time, and yet, according to quantum mechanics, in some sense, that really is a total misrepresentation.
One way to think of this is with an imaginary experiment known as Schrödinger's cat. Here's how it goes. Put a cat in a box with a quantum particle that's hooked up to a sensor. If the particle is in one place, the sensor releases a poison gas and the cat dies. If the particle is in another place, the cat lives. But remember, we're dealing with quantum mechanics here, which means that the particle is in both places. So what happens to the cat?
If quantum mechanics is correct, then it appears that it's physically possible to put the cat into a state where it's neither alive nor dead, but in some unholy combination of those two states.
The problem, of course, is that no one's ever seen a cat in that state. In our world, objects are either in one place or another. It's why we can say exactly where the Empire State Building is, for example, or whether a door is open or shut. But if quantum mechanics is true, then the way that things look is not the same as the way that they really are.
There's two things here that are mind-boggling. One is the fact the cat can get into this state in the first place, and the other is the fact that just by looking at it, we can get it back out of this state. It's as though nature is constantly, every time we turn our backs, nature makes a terrible mess, and then if we turn around, no matter how fast we might, it cleans up after itself, and there it is, just whistling and smiling and looking innocent. And we know because we can create little traps for nature, as long as we deal with only a few small particles at a time, that it's making these messes. But we can't catch it on the fly and actually see the mess with our own eyes, only with these scientific instruments. So the instruments tell us this craziness is going on, but we never actually get to see it for ourselves.
Many theories try to explain this. Maybe the cat is alive in one universe and dead in another. Or maybe it's our own conscious observation which makes the cat snap into a state of being dead or being alive.
One of the interesting things about quantum mechanics is it's so resistant to any kind of sensible solution to its paradoxes. Every one of these options has something about it that makes you want to go on looking. I'm really excited and optimistic that something very important about the way the world works will be discovered in the next 20 or 30 or 40 years that will make sense of a lot of this. And all of the paradoxes of quantum mechanics are just a sign that this still remains to be discovered.
For Philosophy Talk, this is Amy Standen.
I'm John Perry. With me is Ken Taylor. Ken, you told me that our roving philosophical reporter and the person she interviewed, Michael Strevens, were going to clear up all these mysteries. But all I heard Michael Strevens say was that the cat was as puzzling to him as it was to us. He's just kind of got a more sophisticated level of puzzlement. Do we have a guest that's going to clear all this up?
Well, let's see. Our guest today is Jenann Ismael. She's a professor of philosophy from the University of Arizona. She's about to take off on a 5-year stint to be a senior research fellow at the Center for Time at Sydney University, and she's author of lots of stuff, including a forthcoming book called The Situated Self. Jenann, welcome to Philosophy Talk.
Thank you very much.
Hi, Jenann. John Perry here. You've been listening to Ken and I kind of make a botch of what's really weird about quantum mechanics, and you heard Michael Strevens. Why don't you tell us, in words that I might have some chance of understanding, what you see is the biggest differences between the reality quantum mechanics describes and the reality classical physics prepared us for?
Well, philosophers have been talking about this for a long time, and there are really three things that distinguish the quantum world from the classical world. And they've got names. One of them is indeterminism, one of them is non-locality, and one of them is holism. Now, indeterminism is the one I think that's gotten most discussion in the popular literature, and that's the probabilistic character of the way that quanta, which I'll just use as the name for whatever the fundamental entities that quantum mechanics describes are, whether they're waves or particles. What it says, what indeterminism tells us, is that you can't tell from where, for example, a quanta is at one time, where it's going to be exactly at the next moment in time, nor can you tell what its momentum is going to be at the next moment in time. Now, in classical physics, when you knew the state of a system at a certain time, you could always predict with certainty, given the dynamical laws, where it would be at the next time. Indeed, all of the properties would be completely determined by the state at the preceding moment. We don't have that any longer in quantum mechanics. The other thing that's odd is non-locality, and that's something you adverted to just briefly in the intro, which is the fact that you can have quanta that interact at one moment in time and then separate. And they can go as far apart as you like. One can be on Earth, for example, and one can be on Alpha Centauri. And they're no longer interacting once they've separated, but by carrying out a measurement or interacting in some way with the particle here on Earth, you can immediately, instantaneously affect the state of the particle that's over on Alpha Centauri.
Jenann, that sounds like magic.
Yeah, it does sound like magic. Tell us about holism, and then we're going to press you a little bit more on these, because you said three things.
That's right. Holism is closely connected with non-locality, and people have debated about whether, in fact, they're the same thing. But the way to sort of bring out the difference between holism and non-locality is that in classical physics, and indeed in common sense, when you have a complex object, that is an object made out of a bunch of other little things, you know everything that's true about the complex objects if you know everything that's true about its constituents and the properties of the constituents. In quantum mechanics, that's no longer true. You can have a system that's made out of a bunch of particles, and you can know everything there is to know about the particles and the way that they relate to one another, and there's still facts about the whole system that aren't determined by those facts about its parts.
Well, let me ask you about the indeterminism. Let's go back. Let's go back to the first thing you said. So, if you know the position, there's this Heisenberg thing that says you can't know both the position and the velocity, right, at the same time with precision. If you know one, you're cut out from knowing the other or something. Isn't that right?
Well, actually, yeah, there's two things about quantum mechanics that have to be distinguished. One is the fact that the dynamical laws are indeterministic, which means just that you can't know the state at one time from the state at another time. There's another thing that has to do with the uncertainty principle. And what that says is, in fact, that, for example, if you're dealing with two properties that you might think that a particle has, namely position and momenta. The Heisenberg uncertainty principle says that, in fact, it's not just that you can't know, which would be bad enough. It's that no particle simultaneously has definite or determinate values, both for positions and momenta. And indeed, given a complete list of the measurable properties of a system, in general, for any complement of definite values that the system has for some portion of those properties, there's going to be an infinite number of measurable properties for which it doesn't have determinate values.
Okay, so there's two things, but let's go back again to the indeterministic evolution. It's here, and from knowing where it is now, I can't predict with any degree of certainty where it will be. Is that because I just can't peer deeply enough? I mean, if I could look more closely, if I had better measuring instruments, I mean, it's going from place to, one might think, it's going from A to B, and there must be a path it takes from A to B, and if I had enough fine-grained instruments, couldn't I somehow determine it? Or is it just mysterious, just pops around at random or something?
What indeterminism says is that the laws don't tell us. So you might still think that the particle has a definite trajectory. It's just that our laws aren't very good at telling us, given the state at one time, what the state at the next time is going to be. So, for example, you might just think that, everything, in classical physics, we got accustomed to thinking everything evolves by laws that perfectly determine the way that something is going to be, given the way it was at the previous time. And quantum mechanics tells us, well, no, the laws are a little bit weaker than that. They just don't tell us for sure where something is going to be. You might still think that it is at a definite place, but our laws are just they behave in irregular ways that keeps us from predicting where they're going to be at one time.
Okay. So this is John. Let's just review a little bit. So now here we are in our Newtonian world, and our favorite example is a billiard ball. And a billiard ball has a position, and I strike it with a cue. It has momentum, and where its position is determined by where its momentum is and what direction it's going. And there's certainly no problem in kind of locating it, both position and velocity at the same time, right? No problem at all. And that Newton said that the whole world is like that, right? Now, we get it down to the size of a golf ball, it's still like that, right? We get it down to the size of a marble, it's still like that. But when we get it down to the size of one of these gluons or photons, you're telling us it's not like that. It doesn't have both position and momentum. So is it a very strangely operating billiard ball-like thing, or has it become something completely different?
Jenann, I want you to contemplate that for a bit. I want you to contemplate that.
Okay.
You're listening to Philosophy Talk. Our subject today is the strange world of quantum reality. Our guest, Jenann Ismael, professor of philosophy from the University of Arizona and the Center for Time at Sydney University.
We're discussing some of the major differences between classical and quantum physics, between the world of everyday things and the world of little photons and muons. If you find quantum mechanics a little puzzling, you're not alone. Physicists and philosophers have been struggling over the interpretation of quantum mechanics since its inception, and we'll turn to some of those issues when we return. We'll take calls after the break at 415-841-4134.
That's 415-841-4134. Collapsing wave functions, many worlds, and your calls when Philosophy Talk continues.
Thomas Dolby and quantum mechanic. I'm John Perry. This is Philosophy Talk.
The strange world of quantum mechanics. I'm Ken Taylor. Do you understand quantum mechanics? If you do, give us a call and help us explain what's going on to those of us who are quantum challenged, like me. And if you don't, give us a call too, and we'll help clear up your confusion.
The number is 415-841-4134. That's 415-841-4134. Outside the Bay Area, you can call toll-free at 1-800-525-9917, 1-800-525-9917. And finally, you can email us at comments@philosophytalk.org.
Yeah, and our guest is Jenann Ismael. Jenann, just before we went to break, you were going to answer John's questions. He was wondering whether we should think of quanta like billiard balls or in some other way, and you were about to tell us how to think of them.
Actually, there's one confusion that needs to be cleared up, which is there's two separate types, and it's a common confusion, so it's worth clearing up. There's two separate types of weirdness, and quantum mechanics has them both. One is indeterminacy, and one is indeterminateness. Indeterminism and indeterminateness. The way to bring out the difference between them is consider your favorite erratic friend. Let's call her Mary. And let's suppose that Mary, although she has definite position at any given moment in time, she behaves so erratically you don't know what she's going to do from one moment to the next.
Now, how did you know? How do you know Mary? I mean,
You're not Mary in disguise, are you?
I am Mary, actually.
Okay, I see.
Okay.
Autobiographical. Go ahead.
That's right. So Mary is behaving in an indeterministic way if you can't predict her behavior at one moment, given her behavior at the moment before. Now, quantum mechanics does have that feature, and that does distinguish it from classical mechanics. There's a whole new can of worms, though, that's opened up if you deny that Mary has definite position at any given moment in time. Quantum mechanics also denies that, at least on the standard interpretations. It says not only can you not predict the state at one time from another, it says it's in general true that any system whatsoever does not have definite values for all measurable quantities.
Wow. So, Jenann, let me ask you kind of a meta question here. Now, is it that quantum physicists and philosophers of science like yourself that really understand this stuff have no problems with that? It's just hard to digest for us ordinary folk? Or are there some questions of what it all means that still remain when you've got the mathematics and the science under your belt?
I mean, let me press this. What does it mean to say that a thing has no definite position? I mean, come on, it's either here or it's not there. It's logic. Doesn't logic just dictate? It's either here or it's not here. I mean, what does that mean?
Well, it depends. I mean, when you said, do we really understand it? The question, one thing that quantum mechanics really puts pressure on is what it means to understand something. One reaction that one can have to quantum mechanics, and I think it's one that a lot of physicists have, particularly people who are quite adept with the mathematics and who know how to apply the mathematics to predict the results of measurements, is, look, our ordinary concepts, our concepts of space and time and matter, are concepts fashioned by interacting with medium-sized dry goods, the kinds of things that we bump up against. When you get down to the level of quanta, those concepts simply break down. So it might be a matter of the logic of our language or the logic of our concepts, that things have to have definite positions and definite momenta at all given moments in time, and that all questions of the sort, where is it, should have an answer. And it might just be, and maybe it's not that surprising, that when we get down to the level of quanta, those concepts simply break down. You might ask, well, what goes in their place? Maybe we should just acquiesce in speaking quantum mechanics. We should cease to talk about positions and momenta and trajectories of particles, start talking about quanta, and start talking about measurable quantities, or what in quantum mechanics get called observables. And just let the logic of the theory, the mathematical relations between those that are given us by the theory, dictate what we're allowed to say, the kinds of inferences we're allowed to draw.
That's John's remark at the opening. Quantum mechanics rules. Common sense rules. Instead of help me if let's make sure I got this right. So, thing that doesn't have a definite position has a kind of probability distribution, right? What's called a superposition, right? There's a probability of it being here, a probability of it being there, a probability of it being there, or something like that.
Right. It's called the wave function. The wave function in quantum mechanics is what tells us the state of the particle, and we describe that by drawing out of that information about the probability with respect to which we're going to see We're going to find the particle, for example, at a definite position if we carry out a measurement on the particle.
Yeah, but
and that's true.
Wait a minute, Jenann. You said the probability that we're going to find it. But when you got to the other side of finding it, that sounds like that's common sense again. We're going to find it at a certain place. I mean, if it's telling us the probability that we're going to find it at a certain place, doesn't it have to have a certain place when we find it? This is, I guess, the collapse of the wave function, which I don't understand at all.
Right. It does have a definite place, and we know for certainty it will have a definite place when we carry out a measurement. So really, the mystery of quantum mechanics is all about, and I'm going to use a nice phrase I take from John Bell, all about what happens in the limbo between measurements. Nobody doubts that quantum mechanics predicts with certainty that when we carry out a measurement, we're going to get a definite value for position, we're going to get a definite value for momenta, things are going to have properties for definite values for any property that we care to carry out a measurement on. The question is about what happens in the limbo between measurements, and by definition, that's not something we can carry out a measurement to find out.
Well, you know, when I was a kid, they first came out with refrigerators that had lights in them, and I spent hours closing the refrigerator door trying to see if the light was on or off. But there was a contradiction because, of course, once the door was closed, I couldn't see in the refrigerator. It sounds like quantum scientists are in that same problem.
Jeff in Santa Clara is on the line. Welcome to Philosophy Talk, Jeff.
Thank you. Good morning.
Good morning.
My degree is in physics, and I worked for a number of years on geophysical problems, and we took a different approach. We approach science as models. You build models, and when they are useful, you use them. When they're not useful, you discard them. As to whether they are true or not, it's not a question you ask. For example, if I model an electron or a proton or any particle as a wave, I now have an artifact. That is, my model says it's a wave, and therefore I get certain behaviors, and I can look for whether or not certain experiments prove that behavior. But that doesn't mean it is real. It means it's useful. And even Schrödinger's equation was derived not from first principles, but from a search for a belief that there would be a unifying equation between what's called the Eikonal equation, which is a wave equation, and the Lagrangian, which is a mechanical equation. And so he said, if this equation exists, then it would have the following properties, and then they tested those properties. The first one being proven predicting the states of hydrogen. It didn't mean it was real. It meant
okay.
Jeff, I get your point. You think that the mathematics of quantum mechanics is beautiful. It makes predictable. It makes predictions borne out by the evidence, but it's just a kind of calculational tool, Jenann. And I guess he thinks there's no kind of metaphysical reality behind it, beyond its ability to just predict these observations. What do you think about that?
Well, he's certainly right that quantum mechanics gives us a mathematical machine for generating predictions, and that the predictions are with a precision and a range that is completely unparalleled in the history of science. It gives us predictions that are accurate. One can always take the approach that he's suggesting, namely that, well, that's all it is, a mathematical machine. But philosophers ask other questions, and they've looked in the last couple of centuries, in fact, since the 17th century, partly to science for answering those questions. And those questions are, well, what is the world made of? What are its parts? How do they interact? And classical physics gave us answers to those questions. Now, if you're looking to quantum mechanics for something like answers to those questions, then you do have a problem. You do have a problem about understanding the underlying ontology of the theory. And the closer you look at the way that quantum mechanics tells us that that those particles behave when we look, the harder and harder it becomes to understand not just how the world is, but how it possibly could be on the microscopic level to produce those behaviors.
Let me slow you down a second. You said understanding the underlying ontology. What do you mean by that?
What's an ontology?
Just an answer to the question of what are the parts of the material world? How do they interact and how do they evolve? What is it on the fine-grained level that explains why things look and behave the way they do on the level that we actually see?
Well, Jenann, let me take you back a minute to Ptolemy versus Copernicus. As I understand it, the Ptolemy...
We're going way back.
Yeah. There were these models with epicycles and epicycles of epicycles that did a very good job predicting our observations about the stars and the planets. But scientists became, or at least people who looked into it at the time, became more and more, less and less committed to them as a description of reality, and talk very much like our caller, Jeff. These are just models that help our observations. And then, kaboom, there was a whole new way of looking at it that made sense of the models. Now, is there something like that that's going to happen with quantum mechanics?
I think I'm less optimistic than Michael Strevens about the idea that there's going to be something that happens in the next 20 years, let alone the next 100 years, that is actually going to resolve all of the difficulties. I think a physicist said once, that problems don't get solved in physics. It's that the people who thought that there were problems there die out. A new generation comes along. And there's a part of me that thinks that that's going to happen in quantum mechanics. There really has been a conceptual revolution to some extent that teaches us that our ordinary concepts of space, time, and matter just don't apply on the fundamental level.
Joe in Oakland's on the line. Welcome to Philosophy Talk, Joe.
Hi there. I heard you talking about something called the collapse of the wave function, and that involves an observer. And I'm always wondering, does the observer have to be a human being? I mean, if I walk around with my voltmeter measuring things, is the voltmeter part of the system, or is it part of me, the observer? And could the observer be an animal, a monkey, a chimp, or maybe even a cat? Or could the cat collapse his own wave function?
Yeah, or maybe even a meta question. Is there a determinate answer to where the observer ends and the quantum system that's observed begins? How about that, Jenann?
Thanks,
I like
Joe.
that even better.
Thanks, Joe. What do you think, Jenann?
That was canny of you to rephrase the question that way, because the answer is quantum mechanics simply doesn't tell us. There's absolutely nothing in the formal mathematics of the theory that tells us if collapse occurs, when exactly it occurs. All we know from experiment, obviously, is that when we open the door, the light is going to be on. We don't know whether it stays on for a little while after it's closed and then goes off. We don't know whether it stays on the whole time when the door is closed. We simply don't know, and we simply can't tell. And it's the nature of the beast that there's no way to determine it experimentally.
Jenann, thanks so much for returning to my metaphor, because it makes me feel good about the hours I spent as a child trying to figure that out. Our old friend Pete in San Francisco has sent us an email. Hi, all. Is the question of scale an important one when thinking about quantum mechanics? Is it possible that there are very different sets of physical laws for the very small and the very large? Quantum mechanics on the one hand, Newtonian on the other. And can coexist with peace, love, and understanding? Let me add a little to that question. I mean, forget about Newtonian, just the general theory of relativity. Does it really peacefully coexist with quantum mechanics? Is it hard for us to understand, but the physicists have this all figured out?
On the second question, that's a big open question. It's a big open question right now that hinges on complex mathematical questions that's really unresolved. Some people have held that there really is a deep conceptual problem with unifying the theory of gravity with quantum mechanics. But there are live research programs that hold out a lot more hope for actually carrying out that reconciliation. The situation in quantum mechanics is very different, in standard quantum mechanics is very different, because really there's no mystery, there's no real technical mysteries. We have the mathematical framework, and the problems there are inherent in the framework. So it's not that it's an open question, it's that we know what the nature of the problem is and we simply don't know how to resolve it. Going back to the questions about whether there are just two different types of laws, one that describes how things work on the microscopic level, and one that describes how things work in interaction with, say, measuring devices, or perhaps on the macroscopic level, or even perhaps going back to the question of your earlier caller, maybe just when they're interacting with conscious observers. The problem with that is that we have to think that whether you're talking about measuring instruments or conscious observers, we're made out of the same stuff.
Yeah.
That quantum mechanics describes. So if there are two different types of laws that govern us, there really is a deep problem there.
Well, couldn't it be like, relativistic physics versus classical physics? I mean, at slow, when you're not moving very fast, when you're not near the speed of light, then Newton's laws look pretty good. I mean, the relativistic correction is still there, but, it's small. Maybe could it be that somehow, the classical world emerges out of putting a bunch of quantum stuff together, so when you get really big stuff, the quantum stuff just kind of becomes small and negligible? Could it be like that?
It could be. And some of the most promising interpretations of quantum mechanics or ways of understanding quantum reality do get us something like that result. There's a theory by Girardi, Ramani, and Weber called GRW that predicts exactly that when you get large numbers of particles in interaction with one another, behaving in accordance with the quantum mechanical laws, it's almost inevitable that they'll start behaving classically for reasons that they try to draw out from the theory. So there are interpretations of quantum mechanics that do get that result and try to explain the discrepancy between classical and microscopic or quantum behavior in that way. But notice what you're doing there is you're not imposing conceptual framework that we usually apply to the macroscopic level on the quantum level. It's rather you're drawing consequences out of the quantum conceptual framework that explain why our ordinary concepts apply in the limited range within which they do. Yeah. So you're still acquiescing very much in the ontology of quantum theory.
Ed in Berkeley's on the line. Welcome to Philosophy Talk, Ed.
Hi. I knew it was rather uncertain as to whether I would be able to speak or not.
But you did. So your wave function just collapsed.
Which proves something. I'm not quite sure what. But when we're introduced to quantum in the first case, there's this experiment. I think Feynman does it too, where you look at the electron, and in order to look at it, you have to hit it with a photon, and when you hit it, you knock it in some direction, so you don't know what the momentum is. Okay. Well, if you hit it with the photon, you'll know exactly where it is. Let's say I know you won't, but let's say maybe that's the problem. If you hit it again a second time, you will know what the momentum was between the time you first hit it and the time you second hit it. Now, you will also, during that period of time, know exactly where it is at every moment. And in general, if it's experiment bound, then why isn't it more devoted to the experiment? If it's non-experiment bound, why do they use that example all the time?
Well, that's a great question. In other words, as I understand, you're talking about these big accelerators like the Stanford Linear Accelerator, the Circular Accelerator at CERN, and these guys get all these results and all these little marks on cloud chambers by aiming these little particles at each other. But Jenann's telling us they're really not particles. Is there a problem there?
Well, I'm going to let you contemplate that one too, Jenann, for a minute. You're listening to Philosophy Talk. We're discussing the strange world of quantum reality with Jenann Ismael from the University of Arizona and Sydney University in Australia.
You know, there's a lot of learned listeners to public radio, and we're getting nice calls from some of them. Join the conversation, whether you're learned or not. 415-841-4134.
That's 415-841-4134. We'll get to more calls and more emails when Philosophy Talk continues.
She blinded me with science.
Thomas Dolby, she blinded me with science. I'm John Perry here for Philosophy Talk, the program that questions everything.
Except your intelligence. You know, I had a quantum once, and I couldn't find a mechanic to fix it. I'm Ken Taylor. We're discussing the strange world of quantum reality with Jenann Ismael. Join us by calling 415-841-4134. That's 415-841-4134.
Or outside the Bay Area, call toll-free 1-800-525-9917. That's 1-800-525-9917. Or email us, comments at philosophytalk.org. Jenann, let's pick up where we left off before the break. We had a caller, and I was expanding a little on that. So we have these big experiments that take place at places like Stanford's Linear Accelerator or nowadays at CERN, where people seem to aim particles at each other and see what happens when they hit. I mean, I know there can't be any deep problem there, but for some of us there's kind of a superficial problem. How does that make sense if these things are really not particles at all?
Well, we know they behave in a particle-like way when they interact with macroscopic measuring devices. And so there's no problem about what we're going to see when we collide them with one another or we collide them with something that somehow allows us to extract information that we can read about their positions. Whenever you have a measurement that allows us to extract information about position, what you've got is an interaction. You've got an amplified effect, and it's the process of amplification which somehow generates information about a definite position, or somehow, changes the state of the particle in such a way that it now has a definite position. So to go back to your caller's question, actually put his finger exactly on the beast of quantum mechanics, which is, look, you can't carry out science, even if you carry out a measurement on position at every point in time in the history of a particle, which is itself mechanically impossible. But just suppose you did that. What you couldn't do is carry out simultaneous measurements of position and momentum. Now, physicists, Bohr and Einstein went back and forth about this, trying to devise increasingly ingenious experiments. Einstein was the one that was trying to devise these experiments, and Bohr kept showing him why they failed, but ways of determining indirectly both positions and momenta. Now, the weird thing about it, and it gets more and more mysterious, the way in which you see continuously that no matter how ingenious you get, quantum mechanics fouls an attempt for systematic reasons to simultaneously determine values for positions and momenta, that the theory is really, really tricky. If your caller was able to devise an experiment that it did in fact allow us to predict simultaneous values for position and momenta, he would get a Nobel Prize.
Oh.
Nobody thinks it.
Yeah.
Nobody thinks
Hey,
that one would be able to do that.
You hear that, Ed? I hope you're still around. Or Jim, I can't remember who that was. I think it was Ed. Hey, let me ask you a question. Speaking about, you talked about, one of you or the caller previously talked about the trajectory of the thing. As I understand it, I measure this position of this thing now. I do some measurement, right, and say it's here. Now, if I try to figure out how it got here, what trajectory it traveled to get there, I can't answer that question, and because it simultaneously traveled all these different possible trajectories or something like that. Is that right? Do I understand that right? When you think about the past of a thing that, say, I'm going to measure it now, boom, and it's here, right? Mm-hmm. How did it get there? Well, can I answer that question? By what path it got there?
I can tell you in quantum mechanics. I can tell you what the state of the thing was at any given time, and I can tell you, given that state, what probability you would have for finding it if you carried out a position measurement here rather than there. What you can't do is fill in the story in such a way that you assign a definite value for position, describe its a completely determinate trajectory. So what you can't do is you can't, answer all the questions that you might have about it applying our ordinary concepts.
Well, let me see if I understand it. Suppose that we've got Ken and his evil twin Ben, and they're identical, right, quanta, right? Just, one's a meson, the other's a meson, or whatever they are. And we collapse their wave functions at a certain point, and we see Ben is in room A and Ken is in room B. And then we come back a minute later, and we've got one quanta in room B and one quanta in room A. If it was an ordinary size object, we could say, well, did they stay in the rooms or did they shift rooms? They're twins, we may never know, but at least it's a reasonable question. Would that be a reasonable question if they were mesons or whatever those little things are?
It's not one that quantum mechanics gives us an answer to.
So they just don't use this concept of the same thing, either moving or not moving, from room A to room B?
I'm going to ask you one last question about this. Is that because because in the nature of thing, there just is no answer? There's just no determinate trajectory it took? Or is that because, there is a determinate trajectory, but quantum mechanics is just too coarse of an instrument to tell us what's really going on?
It's psychologically irresistible to think the latter thing. And Einstein, to his dying day, thought the latter thing. That is, you've got a coarse description of nature, and there's going to be a way of filling in the blank spots in such a way that particles, for example, always have definite trajectories. There are definite facts of the matter about whether the particle you're looking at now is the same one you saw a little while earlier. Definite facts about how it got to where it was, given where it was before. It takes a lot of sort of interacting with the mathematics of the theory to see that, in fact, you cannot fill in the blank spots in the theory that preserves all of your classical intuitions. it's mathematically impossible. And there's a battery of increasingly strong mathematical results that show that you're not going to be able to do that.
All right, Jim and Alameda's on the line. Welcome to Philosophy Talk, Jim.
Right, thanks. My question is, in some empirical sense, can you infer from the indeterminate qualities of quanta to some kind of justification for a free decision?
So in other words, there's this classical problem of free will that we have as humans, and if we're determined, how can we be free? And you're saying, can quanta somehow solve that problem for us?
Thanks, Jim. Jenann, lots of people think things like that. Quantum mechanics, I thought you talked about the lull between measurements or something like that. Quantum mechanics leaves room for free will to act. Some people also say it leaves room for consciousness in the material universe because this collapse of the wave function has to be a conscious observer, so the theory builds in. How do you respond to stuff like that?
Let's back up to the problem of free will. The way that the problem of free will got sort of its purchase in philosophy is when science, started, when we were working with the classical worldview, so Newtonian mechanics, we started thinking of people, and we think of people as just physical systems. We had these laws that told us that in principle, if you knew the state of the system at one time, and you knew all of the facts about the forces that were impacting on the system at that time, you could with certainty predict how it was going to behave all through, at the next instant and the instant after that and the instant after that. And people thought, what sense does that make of the idea that we actually determine our actions, that we act freely? So the context, the philosophical context within which the problem of free will originally arose was a deterministic one, and it looked like it had a lot to do with the fact that we had these laws that predicted with certainty how a system would behave given its state at one time. Now, and that has led some people to see the indeterminism of quantum mechanics as possibly making room for free will. But reflect on that for a second. Suppose that the quantum mechanical laws are in fact the true ones, and that we are just quantum mechanical systems, and that what happens actually is that we're in a state at one time, and then something completely arbitrary and deterministic occurs within us that determines how we're going to move from one instant to the next. Does that really help us?
I don't think so.
Think that we're free.
So the question is, why would we be better off having quanta doing this than just having a deterministic roulette wheel?
Exactly. Why would an arbitrary event like collapse of a wave function in your brain make you any more free?
Well, I think the intuition might be, I don't know, that it can't really be probability all the way down. Because look, if two events are probable, if there are two outcomes with a certain probability, well, one's going to happen and one isn't, right? Well, what makes the one that happened, say the low probability one happened, what makes the one happen that happened? Well, it can't just be the bare probabilities because they were there to begin with. So something extra has to be added, I think people think. And that something extra, physics doesn't tell us what it is. It's the human will. I think that's the kind of intuition.
Well, there's other people like Robert Kane that have the intuition that phenomenologically we're most clear about freedom, and when we have this case where we seem to have these competing things that just don't settle it, and that maybe there's some, it does seem kind of odd if determinism was the problem for freedom, why removing determinism shouldn't be part of the solution.
So are we giving any aid and comfort to the person who wants to find room for freedom in quantum mechanics by talking this way, Jenann?
If you think, as you were suggesting, that look, what we really need to do to explain indeterminism is to allow that there's something outside of the material world that determines when we've got something that's physically indeterministic that actually determines it. That connects back to the question of whether consciousness is somehow entering from the outside and collapsing wave functions. If that's the view that you have, then yes, the indeterminism of quantum mechanics leaves room for a view like that.
But there's quite a gap between the science of quantum mechanics and that view.
Obviously. I mean, if quantum mechanics is right, vacuum cleaners are as indeterministic as people. Mm-hmm. They behave in just as indeterministic a way. So the mere indeterminism.
Well, I think you know my vacuum cleaner too.
Yeah. We've got Bill. Bill's on the line. He'll probably be our last caller. Welcome to Philosophy Talk, Bill.
Hi, thank you. Well, let's see. You mentioned two sets of laws, quantum and classical. But aren't there three, considering relativistic laws? Or does one just slide into the other, as you said? or are there cutoff points between the three? And also then, Newtonian physics seems to have pervaded our philosophy of the world. A plus B equals C, but that's not so in the quantum world. You can shoot a particle down and bounce it off a target, and the particle can come right back down to the tube that shot it out. Could this be an explanation as to why things backfire in our world, in our plans, or like what are some of the practical implications, philosophical, of quantum mechanics to our everyday Newtonian world?
Thanks, Bill. Jenann, if you can answer that kind of briefly, because we're about out of time.
One thing
I know it's a
large
thing.
It is. So very briefly, first, there's much, much more mundane explanations for why things go wrong in our world. I think the second is, when I talked about classical physics, I was including relativity. Relativity is very often in these contexts used to contrast with quantum effects. As for some of the weirdness of quantum mechanics, what kinds of practical implications does it have? It's unclear. It's unclear right now.
Jenann, it's been really, really, really great having you on Philosophy Talk. Thanks for joining us.
Thank you so much for having me.
Our guest has been Jenann Ismael, professor of philosophy from the University of Arizona, research fellow for the next 5 years at the Center for Time at Sydney University, and a really fun person to talk to.
Jenann, thanks so much for joining us. And we also want to thank all the callers we didn't get a chance to talk to, and a couple of emailers that we didn't get a chance to read their emails.
So, John, are you in a state of quantum flux, or is your mind settled about these issues?
Well, Jenann is a very brilliant person and very good at explaining things. So I feel I learned a lot today, enough to make me want to go and read another yet watered-down book for lame brains about quantum mechanics.
There's a place that you can go to read all kinds of articles written for basically a lay audience, but will take you from the beginning to the middle to the end. And that's the Stanford Encyclopedia of Philosophy. There are a ton of really good articles on quantum mechanics, its interpretation, stuff about consciousness, freedom, the mathematics. It explains it to you in an easy way. All kinds of good stuff there. So
yes, go to the Stanford Encyclopedia. Thanks for that plug, Ken. And you know, the thing about quantum mechanics is it is basically mysterious. And there is a certain tendency in philosophy to take all the mysteries we have, quantum mechanics interpretation, the self, consciousness, free will, the nature of right and wrong, and think that since they're all mysterious, they must all have the same solution. But I do think we need to resist that. There's plenty of mysteries to go around.
Well, I think that's right. But, you know, I'm convinced from delving into this and talking to people like Jenann and other people and listening to talks about this stuff over the years, that quantum mechanics is really deep, a big, huge conceptual revolution. And I think the thing that Jenann said, that we need maybe to reconfigure our common sense conception of the world, learn a new way of talking about the macroscopic order and human beings. I think that's a deep and important thing.
Well, you know, with the 10, 20, or 30 years I have left to me, I may just leave that to you younger folk and keep thinking about the world pretty much the way me and old Al Einstein did for the rest of my life.
Okay, if you want to continue this conversation, check out our blog, the blog.philosophytalk.org, where our motto is cogito ergo blogo.
Philosophy Talk is a presentation of Ben Manila Productions and the trustees of Leland Stanford Junior University.
Our executive producer is Gordon Earl.
Special thanks to Rujan Shen, Nicole Sawaya, Ben Tempchin, and Alan Farley.
Support for Philosophy Talk comes from the Pacific Division of the American Philosophical Association.
Also from various groups at Stanford University, the Friends of Philosophy Talk, and the members of KALW Information Radio San Francisco, where our program originates.
The views expressed or misexpressed on this program do not necessarily represent the opinions of Stanford University or of our other funders.
The conversation continues on our website, www.philosophytalk.org. I'm John Perry.
And I'm Ken Taylor. Thank you for listening.
And thank you for thinking.